Okay, on our front page here with the 338 Training Squadron Dark Knights, you'll notice off to the left I enlarged one of the cases. This is a case that you're going to be working on a lot. You can see the laptops on top of the case. You'll see that there's one device, I want to say about a third down, that's not like the others. That's the NSM50 that you guys will be working on starting tomorrow afternoon. So let's get right to it. We're going to start where we left off, which is the Nyquist Theorem. Again, 2 times the highest audio. In our case, it's going to be 4K. The reason why 4K is we're going to double that. That's the way PCM is. And we were explaining Audacity before Aaron Bridges had to leave. That audio program is probably one of the best freeware I have ever seen in a very long time. They're getting really good at it. Now, the reason why I brought up Audacity is there's a place in there when you get ready to save your audio, whatever it is as an MP3, you have some selections there. Everything from 8K, and that's a sample rate, all the way up to 320K. It is insane how they work that. So when you take a look at PCM, we don't need to be at 320K. We only need to be at 8K. Why? We're only doing voice. With the 320K, you're trying to make the best possible quality that is, in this case, Audacity capable. I'm sure there's other programs that could do better. But the nice thing about Audacity is you can manipulate. It's got a lot of filters and manipulations in it. You don't need to do that with audio. Now, back when we first had CDs, you know, it started out with 8K for a sampling rate. And then it went up to 16, then to 32, and then it went up to 64. And after that, CDs started becoming an old school, and you started hearing about MP3s. Like the, what is that, an iPod started coming out, and they started saving everything to WAV files with the lossless and so forth and so on. So there's a lot of technology that goes with this Nyquist theorem, but Nyquist is where it all started at. So when we look at something called pulse code modulation, there are 3 steps involved with it: sampling, quantizing, and encoding. The first step is sampling. Now, you guys have already seen the term sampling, where we're going to take sequentially the analog signal and we're going to sample it 8,000 times a second. That's pretty, that's a lot of information in that 1 second. Now, the way we use this is we have this amplitude measurement, and they call this a pulse amplitude modulated section, where it's all done in sequence. But as you can see, my voice, and if you hadn't noticed, for those of you that have a computer and can see in the bottom right hand side where my face is, you will see a audio bar that's going up and down and all that kind of nice neat stuff. That's pretty much what a PAM looks like. So let me change over here to this one, and you can even see it better as I go up and down in the voices. Nice to have these gadgets around every now and then, right? So that is our first step, is we're going to sample that analog waveform using that PAM, not Peter Pan, but PAM, as in the spray. We have PCM step 2, which is called quantization. Now, because we've sampled every one of these pulses, we're going to start giving it a number. Now, if you can picture the number that we're going to give, it's like a graph paper. And I hope everybody has seen a graph paper before. It is both horizontally and vertically sectioned in equal squares, so to speak. So what we're going to do is with each one of these pulses, we're going to put it sequentially on that graph paper, and that's quantizing. Now, they call the table that we put it on a quantization table. It is approximately, well, I shouldn't say approximately, it is 256 steps. We go from 0 to 127 in the positive side and 0 to negative 127 on the logic low side. Now, if you add those two together, you don't come up with 256 steps. That number right there is incorrect, period. It should be 255. And why is that? Let me write this down because I just now realized I needed to correct that.
Is it because of the bit rate, sir, or the?
Okay, what does an 8-bit word total up to?
I have no idea, sir.
Okay.
126, 128.
Yeah, 1 to
So
128. So if you go 1 to 64 and add all those together, you come up with 127. You add 128, what do you get? 255. So that's the reason why that number is incorrect. I've been meaning to change it, but every time I try to remember it, I forget. So you got 255 steps, or 255 steps supposedly. Well, that's not the case, and I'll show you in just a minute. We have, again, the positive and the negative side. So you have 0 in the middle, 127 from 1 to 64 will identify that 127, and in the negative part you'll have a negative 127. You're going to scratch in your head, okay, this is not making any sense yet. Au contraire, give me a moment. All right, so we have two different types of quantizations. We have uniform and non-uniform. With the graph paper, that is uniform, but there's a problem. When you have these pulses, let's just say that in this case it's between the 3 and the 4, you just can't put 3.5 because there's no way to do an 8-bit word that has 3.5. So you literally got to round it. You either round it up or you round it down. Just like with anything else in math, 0 to 4 you round down, 5 and above you round up. So this quantization is now called an error when we have to round. The quantization errors happen in uniform quantizing, and that's that equal space. Well, what they did come up with is something to help out with most of the quantization errors is non-uniform. What they looked at is said, you know what, the bulk of everybody's voice, we're talking masses here. Where are they? Well, it's in the middle part. So what they did is they squashed all these lines down, still keeping them the 127 lines, and put them mostly in where your human voice is going to be. So that helped out with the quantization errors. It doesn't correct for everything. Now, the lines that get squished, you got at the upper end and the lower end, you got to start spreading them apart further. So what does that mean? It means that people with very...
Hello? Can you hear me?
Yeah, we can hear you. What happened? Chung, what happened? He got lost there or something. Chung, you okay? Wonder if he got... Okay, negative on the voice if you're trying to key up.
Can you guys hear me now?
We sure can now.
Yes, sir. Things are. Sorry, I don't know. Something just lost connection.
Okay. And that Wi-Fi is lovely there, eh?
Yes, sir.
Okay, so getting back to the non-uniform quantizing, as you go up, again, that 127 and negative 127 are the same spaces. It's just that they squashed most of the lines where the human voice is. Now, if somebody has a higher pitched voice, they're probably going to start to see some rounding of their voice. In other words, quantization errors. Anybody who had that deep vibrato voice is probably going to have the same issues. So you can see where non-uniform corrects for most of the quantization errors, but doesn't correct for all of them. Now, with that in mind, we've eliminated most of the quantization errors by non-uniform quantizing. We're going to go to the third step. Now, this is where that 8-bit word comes into play now. With the 0 to the positive 127 and the 0 to the negative 127, it still equates to 127, 1 through 64. Well, that last bit, the 8th bit, the 128th bit, that's where you can tell whether it is the negative side or the positive side. So when we convert all of this information over to a binary digit, or encoding to give us that 8-bit word, we're going to take something like this. So you can see the table on the left-hand side as far as the quantization and sampling that's going on there. But on the right-hand side, in that table there, you can see how the words are coming up to play, this 8-bit word. So anything that's a positive 127, you can see from 0 all the way over to the next to the last digit, that's the information that you need. Well, the last bit on the left-hand side tells us whether or not it's a positive or negative 127 in that stage. In our case, if we look at the number 2, 0, number 1, 1, which would be 2, and the rest, 4, 8, 16, so forth and so on. Then you get to that last digit. The 0 represents a positive 2. I don't know why they did that. Couldn't tell you. It's an engineering thing. So anything that you see negative 127, as you go down the table there, you'll see a negative 2, negative 4, and that all of the 8th bit numbers are 1s. So now we've completed the 3 steps. You got sampling, you got quantizing, and you have encoding. We used to be able to get this digitation EXE, which gives you an idea how it works. I have the application, but I can never get it to where I can fully display it on our table. So I'm still working on it. Give me a chance in the next couple days to figure out how it's going to play out. It's a pretty neat little how you get from analog to digital and from digital back to analog. That's what it's showing. So next up on the analog to digital conversion, we have frame period. Now, frame period is where and this is a definition, the time it takes for one frame to occur. Well, you saw where we have like frame 1, frame 2, frame 3. We got to sample everything that's in there to figure out where everything needs to go. So that frame period is pretty big. In other words, in our case, we have 24 channels that we need to sample. How long did it take us to sample all 24 of those? Well, in this case, we're going to take the reciprocal of the 8,000 frames a second, and it's going to give us 0.000125 seconds, or 125 microseconds. So what does that tell you? Well, in order for us to sample channels 1 through 24, it took us 125 microseconds to do it for my first frame. When we go on to the next one, which is called pulse modulated sample period, it's the time to take it to sample one channel in any given frame. So 125 microseconds. I want to sample how long it's going to take me to sample one channel. So what you do is you take whatever you got for your frame period and you divide it by 24. In our case, you got 125 microseconds. Well, it's 0.000000528 seconds, or 528 microseconds. So it took 125 microseconds to go through channels 1 through 24, and it took 5 microseconds to sample one channel. So you understand, frame period's pretty big, pulse modulation sample period is very small. So if you were to take 24 times 5.28, you'd probably get 125 microseconds. And the idea behind this is to give you an idea how quick this thing is and how to line up everything. Now, you'll see out in the internet world that when you look at a TDM mixer, multiplexers, you're looking at 24 channels as a standard. That's what they came up with. And when I say they being the industry standards. There are more, there's less. For example, I told you the SCC was a 16-channel multiplexer. So even though they would have 125 microseconds, because it does sample at 8,000 times a second, but I would take 16 into that frame period and probably get a longer time frame. Probably about, I don't know, 7 microseconds. That's what, less than how fast you can blink your eye? So this is all overwhelming. This is the reason why Block 7 is considered one of the tough blocks here in the course. We've gone over general multiplexing terms, talks about data relationships, types of multiplexing, modes of TDM, demultiplexing, signaling formats, analog to digital. So here's the question. What are the 3 self-clocking signaling formats?
I know of conditioned diphase and then RZ polar.
Okay, and can someone tell me what the last one is?
Non
what?
RZ polar.
Well, she said CDI and RZ polar. We're missing one more. What is it? How about RZ bipolar with zero suppression? That's your third one.
Oh, okay.
Make sense? Yeah. So what corrects for the quantization errors, or what corrects for most of the quantization errors? Anybody? How about
uniform quantization?
exactly non-uniform quantizing? Good. What is a quantization error, Airman Richard?
Quantization error, isn't it the error when you're, hold on one sec. The error when you're quantizing and it rounds up?
There you go. Good. Rounding. That causes quantization errors. All right. Crap. Let me, okay. Outstanding. So next one we're going to go over 1 Charlie, 1 Delta, 2 Alpha, and then the NSM Tech Manual. So let's look at 1 Charlie. We're going to identify basic facts about network bandwidth management equipment. Let's take a look. Yeah, we're going to have to deal with bandwidth all the time. So we're going to look at bandwidth allocations, network infrastructure, transmission media, carrier system concepts, and hierarchy. We have 4 types of bandwidth allocations that we go over. One's conventional, demand assigned, dynamic, time of day. The first one, conventional. This is a fixed amount for everybody. The problem is because everybody has a fixed amount, the bandwidth is wasted. Let's take a look. So if you can see in this diagram here, we have 4 users or channels, and each one of them has on their bandwidth 64K. Well, that's a grand total 256. But in our case, only 2 of the channels are being used, but you still have 256K coming out. So you're losing a lot of bandwidth. Next we have demand assigned. This one says, hey, you still get an exact amount, but it's not dedicated, over the whole thing. So when they give an idea about the internet, and this is one way to take a look at as to why everything is asynchronous and you're given so much bandwidth to get in there. Now, when everybody is on, they don't think about that, especially you guys in the dorm, and it's going to get massively, I guess the way to say it is, it's going to get massively saturated with all that information wanting to get online. So with demand assigned, you got one user with 64K, another user with 9.6K, another user with 56. So you have 126 left over, but you still have 256 to fill up. So what it's saying is if I'm doing 9.6K and I'm running a video and it requires 64K, then I have a very good opportunity to use 64K. It's just like the internet. When I described to you that during the daytime from, let's say, about 2, 3 o'clock all the way up to 8, 9 o'clock, you're probably going to be waiting for your time to get on the internet using the TDM method. But when you get past outside of those time frames, now it starts speeding up for you. You can play an online game, and this is the reason why. You're not saturating the bandwidth waiting for time, but you have a set mode. Now, this doesn't go, okay, I'll wait till she gets back. Anybody got any new word on bridges yet?
No, sir, I don't believe so.
Okay. I think this is probably going to be another 1.5-hour session. The other one was close to 2 hours. I got it edited. I just don't have it uploaded yet. So look for at least one to come into the chat. When I say one is this morning's session, I'll provide a link for you. This afternoon's session, not sure yet, but if it's every bit of what we did this morning, it's going to be very, very long indeed. And it takes some time to get things loaded to YouTube.
Sir, is 1C, 1D, 1 Charlie, 1 Delta, 1 2 Alpha, are they part of day 2?
Yeah, no, they're, well, yes, according to your schedule. But what I like to do is I like to get everything done in one day and then go over homework tomorrow morning. So that way you're caught up, you're familiar, you've had some time to rest on it, and now you can go do your labs and still be able to have the information in front of you to be able to study. And it seems to work out. I don't know of any other way to do it because I have classes throughout the rest of the day. So it's a push to get you guys to where, in the classroom, I would probably stop at the PCM on day 1. Day 2 would be PCM all the way up through today's work, and then we would have 2 days to do the NSM and then cramming in the rest of it, and it gets to be very tedious after that. What I've found is if I spin everything up quickly, you guys get the information and you're able to sit back and start resting on it. Seems to be working. So anyway, Hancock is back, so let's do this part. We just got through with the internet. We're going to do dynamic. This one means that everybody together, you're going to exceed your bandwidth. This is what I think has happened with Boingo, but not entirely their fault, because if you guys take a look at how many is in y'all's dorms, we're looking at what, 500, 600, 700 per dorm, and there's what, 3 or 4 or 5 dorms. So you're looking at a couple thousand people there, right in that one little area. Well, think of it as a big, huge fire hose trying to push all that information out on a garden hose. So it's not the information on the base, it's the information trying to get on the base, out the base. So that's part of the problem. Now with dynamic, what they do is it works like the trunking system to a certain extent. They give you X amount, but when everybody is transmitting, it gets crazy. So here you go. You can see that the total amount of inputs is exceeding the total amount of bandwidth. Now with that, it's going to saturate the 256. You're going to have to wait to get online. So that's what's happening in a nutshell with Boingo, but at the same time, it's not completely their fault, but it just goes to show you what could happen. Now this next one is time of day restriction. The easiest way I like to say this is, if anybody's ever watched The Lone Survivor, I'm trying to remember the guy's name. Oh jeez. Anyway, The Lone Survivor, where every time they got to call back to base on a sat phone, it's not doing well, or excuse me, on one of their sat radios, it's not working, because they can't reach the satellite. I guess the guys don't really know how to set those things up, get out of the trees, in other words. But they had certain times where they were allowed to call back to base. That is time of day. You have that priority for that specific time, and I think it was a half-hour time frame that they were allotted for each day while they were out there. So that gives you an idea of what's going on. Network infrastructure. Okay, the big thing is your interchange. The big interchange network. In other words, everybody that's at the dorm gets on a server, and the server sends it out through the internet. And of course, there's more steps to it. The big thing is there's 2 of them out there where you're making that contact. We have the EIA standards. This is how we get the interoperability between devices. In other words, it used to be where Apple products could not talk to PC products, or you had one brand of PC products and they wouldn't talk to anybody. You would literally have to buy their printer and their cable and all that kind of stuff. Well, this is where the electronics industry came into play and just said, you know what, we're going to make sure everybody's on the same page. So no dominant manufacturer goes out there and basically becomes a monopoly. So by doing this EIA standard, this is how everything started working. Now you can talk from between an Android to an iPhone to your PC. It doesn't matter what brand that you got. It all works supposedly the same. Like a Linux can talk to a Microsoft operating system, which is kind of crazy, but hey, it does. So let's take a look at these two. First of all, 232, this is your older style. In other words, dial-up. And if anybody's ever had dial-up, anybody in here ever heard of dial-up before or worked with it?
Yes, sir.
Yes, sir.
Okay, so you know that little and you hear this poing. You can hear it on the internet. That's about
Yes,
as close as you're going to get with it.
That sounds about right.
Yeah, well, for someone, that's what it was, 56K came inside the computers. Nowadays, it's an a NIC card if you got one, if you want one over the internet for your purposes if you're building one. The big thing here is when we look at transmission lines, we have a balanced line and an unbalanced line. The first one is a balanced line. This is where we have a twisted pair, and on each of those lines we're going to send a signal out. Now we're going to take one of those and flip it 180. So one is one way and the other is the other way. So when it gets down to the back end of that, where it gets put back together, because lines generate noise, when it gets to the distant end, when they flop them back into where they're in phase with each other, it cancels the noise out. This is an example of what your noise canceling headphones does. So it takes everything from the outside, and if it gets onto the inside, they take those two and cancel it out. So it just gives you an idea how we've advanced in technology for noise canceling headphones. Next up, we have an unbalanced line. This one is a coax cable. The big thing is everything travels on that center pin. The shield is what is grounded, and it keeps all the noise in that from being on that center pin. So it just gives you an idea of the differences between a balanced and an unbalanced line. Next up, do we have anybody in here that has one of the Block 1 issued computers to you?
No, sir.
Okay.
I believe Aaron Bridges does.
Okay. All right.
I've
Well,
got one, but I'm not currently using it.
well, if you take a look at those, you will find, I think it's a DB25 connection on it, not to be confused with a display port or an HDMI or a C or any of those others, but it's an older style, and what you could do is you could connect up another monitor with it. Or, in our case, back in the day, a printer. Kind of wild, ain't it? 9-pin printers were a big thing. Then we got better. Now what is it? You can get a Cat5 cable, you can connect it up to the internet, or most of our printers nowadays is over the air using Wi-Fi. So that just gives you an idea. Now you will be using a DB connector when you are connecting your BERTS to it. That's a built-in, bit error rate test set. That's a BERTS, better known as an HST3000. That's the name brand of the BERTS. That one I think is 50 pin, and it's going to go on to a NRZ DB connector. Plot thickens, doesn't it? So we have had some things in the past, and I've had to deal with this on the OJ314 console, and they had a lot of digital problems with it, and one of them is they dealt solely with negative logic. So what should have been a 1 is now a 0, and a 0 is a 1, and you just got to try to figure this thing out when it comes to using your logics. I know it sounds crazy, but every now and then you get one with a negative logic. That's just an idea in what possibly you could be dealing with. Now we upgrade to a EIA 530. This one, now you're able to get faster and go farther with your modem, or get to the modem. So in our case, I deal with AT&T, and their central office is less than a mile from me. So I'm able to get pretty decent connection I think mine, the max that you can get with mine is 25 and 5. That's my, I think it's 25 down and 5 up. I think that's the way it works. So it just goes to show you that technology, now when you deal with fiber optic, which I wish we had right now, you're probably going to get faster. That. Next up, we have something called DTE and DCE. Delta Tango Echo, better known as data terminal equipment. This is your computer. In other words, you're generating it from the computer, and your distant end will be a computer. That's data terminal. Terminal being the distance, the source, or the destination. Data communications equipment is the communications that you send the computer or the information from the computer to the communications device. In our case would be a modem or modem router or the Wi-Fi or whatever that we need to do to get that modulated and sent to the distant end. We have 4 different types of transmission media that we go through. Twisted pair, coax cable, those two you've already given a brief overview of. We got fiber optic and wireless. Let's take a look at each one of them. Twisted pair. Anybody know what the difference between Cat 5 and Cat 6 is?
The amount of data they can go through that it can transmit.
Okay, and what's the differences, physical differences between the two?
Is one of them more shielded?
No.
One could hold more data.
Well, yeah, that's what Aaron Chung just said. How about one has more twists than the other? That's the only difference. They figured out a way to use that transinductance to use those twists to get more data through it. Crazy, ain't it? That's the difference between a Cat 5 and Cat 6. More data because of the twists. Next up, we have coax cable. The thicker the coax, the better off you are. The better. And if your shield is grounded, you have a less of a bit error rate segment. In other words, less errors. That's one way to take a look at it. Now, fiber optic, now this is where everybody wants to go to, but I've been hearing that AT&T wants to go to the 5G. I'm not so keen on that because if the over-the-air system goes out, everything goes out. Whereas fiber optic, if you put it in place, put it underground, whatever you need to do, then it's not too big of a deal. I'm just hoping that they get mine here. Like, this is the 3rd year now that they said it would be installed by June, and I've not seen hide nor hair. We have wireless, which is pretty obvious, but we got a problem with some of this when we look at line of sight, satellite, and tropo. We're at the mercy of our adversaries at times when it comes to satellite, so HF is being put in there too, which is beyond line of sight. Satellite is considered beyond line of sight, but it is actually a line of sight system. If you can't get it to the satellite because there's a lot of clouds in the way, guess what? You ain't getting it. So wireless is now becoming the mainstay of everything. We have something called a digital service unit. Now, if you take a look at the picture, you will see we have a DSU and a CSU. Most of the time with your internet providers, they'll have that in one box. So when you call them up and say, I got a problem with my internet, they are going to go to that box. Now, the first thing that they're going to check is what we call a DSU. That is the customer end of this. Now, they're going to ping that DSU. It's going to send some loopback signals to go to your computer, and it's going to send it back to the DSU. That's how they troubleshoot whether it is your system or their system. Now, you'll notice it says AMI, alternate mark inversion. That's that RZ bipolar for you. And then the last side of the house where it says offers customer loopbacks. In other words, it's the user side of the network. But when we look at the channel service unit, I get a lot of people going, well, CSU is a customer. No, no. Get that out of your head. It is not the customer. It is the network side. You're going to see something called RZ bipolar with zero suppression. C is not for customer. C is for channel. Channel being the network. And again, RZ bipolar with zero suppression or alternate mark density with suppression. So there you have it as far as those two systems. Again, they can be put into one box, and normally the first thing that the internet provider looks at is it your side first? Why? Because every, once in a blue moon they get a technician that goes, no, it's y'all's side. Well, how do you know? Because I know how to troubleshoot it. Well, how do you know how to troubleshoot? Because I teach it. And they just, okay, where you see the problem at? It says, well, it's not with your DSU. The CS. Yeah, it's not with the DSU. It's your CSU, the network side. Something's not getting to my end. And for the last one that we had there that I troubleshot, I told them it's got to be the wire to your end, because they were saying, no, we see everything, but it stopped somewhere. Like, okay, ended up it was squirrels eating through our cables. Lovely. So next up we have something called hierarchy. This is how we set up multiplexers for a DSO that is one channel. And you'll notice that we've got a standard 24 channels. This is how this hierarchy is made up. I didn't invent it, the manufacturers did. So with one multiplexer, 24 channels, you get a max data rate of 1.55 megabits per second. That's pretty slow in our books, isn't it? But when you add about 4 of those together into one, you make it a 6.312 megabits, or what's called a T2 line. And then when you add more, you end up with a T3 line and get it even faster. So you can see that our bandwidth and max data rate gets increased as we go up multiplexers. But there is one problem with that. When you get, I think, beyond the 4, there's things called superscripts that start getting induced into the multiplexers and creates error problems. So let's take a look at one of the hierarchies that I found on Google. You can see that we got a T1 MUX, which is a multiplexer. You have channel 1s through 24. You get one of those. You put it into a T2 MUX, which has 4 of T1s going into it. And in order to get a T3, you got to have 7 T2s going in there. And then when you get to the T4, you're going to have 6 T3s going into it. And to get a T5, then you have 2 T4s. So you can see that when it gets from the 3 to the 4, they start going down in multiplexers, but they increase in bandwidth and speed. So we've gone through bandwidth allocation, network infrastructure, transmission media, carrier system concepts, and hierarchy. Questions? Information saturation, right?
Yes, sir. I'm gonna need some serious SIA.
Well, that's fine by me. We just have to make sure we plan it together. And again, if there's anybody out there that wants the SIA, my hours are supposed to be from 8 o'clock in the morning to 6 in the afternoon. But that doesn't always happen. I'm up at 6 in the morning, on Discord, probably at about 6, 7 o'clock, maybe 8 o'clock at night before I sign off. So I'm available. It may take some time for me after the 6 o'clock time frame. So by all means, if you want SIA, we'll give you SIA. That was Unit 1 Charlie. Let's go to 1 Delta. And at this point, I got 1:54. Let's take 5 minutes, come back at 2 o'clock, okay?
Yes, sir. Thank you, sir.
Sure. Excuse me. The 12 NRZ ports, these are EIA 530 ports, D connectors. Gives you an idea of what you're going to be messing with. The 6 T1E1s, there's that location, the 2 ISCs, and the 6 CDI. This is the extract that we will be using here in a few moments after we get through 2 alpha. And of course, going through all of this, we'll get into the TO here in just a few minutes. Let's go on to 2 alpha. We're going to be looking at identify basic facts about the capabilities and limitations of the bit error rate test set, better known as BERTS, not to be confused with Bert and Ernie. You know Sesame Street? No?
Yes, sir.
Man.
Reading us Sesame Street. Bridges, are you a father yet?
No, she's so they've given her something to speed up her dilation and speed up her contractions. Right now she's stable, just waiting. I thought I might as well go into class, told her to call me if anything changes.
Roger that. And welcome back.
Thank you, sir.
Yeah. I think the last 2 or 3 minutes I forgot about pressing the unpause button, so you're going to miss some of that. If you run into some other issues with it, please ask me. I can go through it again. So we're looking at 2 alpha bit error rate test set. Again, 70% on the test. That means you can only miss 12 out of the 40. You're going to be using it tomorrow afternoon for those of you that are, I think, in the first 2 groups. We're going to describe it, take a look at it, and the HST 3000 is the version that we are using. It's about 7, 8 years old. You're going, oh man, another older piece of equipment. Hey, it doesn't matter. You can actually buy this brand new on eBay for about $3 grand, still in the box. Every year they come out with a new model. It does, a lot more whistles and bells, but this is all we need it to do. And if you were to take a look at that NSM, it only looks like it might be a year or 2 old. That's how good it is. So what does it do? Performs tests, loopbacks on a system to analytically analyze the system quality as it travels across the network. Yay! You can see it does it alone or alongside the mission traffic. The big thing here is the HST and what it does. What does it do? End-to-end testing, which would be DTE, and bit error rate testing. Now, I don't know who your lab instructor is, but I like to do the bit error rate test. And the last time I seen, we only have one in there because there's 2 block 9s going, and we didn't order enough HSTs to do the NSM. So we only have 1 in there instead of 2. I like running 2, but hey, stuff happens. The 3 test modes with this bit error rate test set is DTE, which is data terminal emulation. In other words, it simulates the computer. DCE, data communications equipment. It's going to simulate the modem. And then just to take a look on the outside looking in and not bothering anything, you're going to use monitor. So I do think that the BERTS is being used as a DT emulation in the setup in lab rooms. So we've gone over general description, HSTV operation. Any questions? That was a short one, right?
Yes, sir.
So if you guys would go ahead, pull up your operator's instructional manual for the NSM. It is 31R2-2 Tango Sierra Charlie 179 extract or -2 extract NSM 50 operator's manual. It should be a PDF.
Can you repeat that one more time, sir?
Sure can. 31 Romeo 2 -2 Tango Sierra Charlie 179-2 extract NSM 50's operational manual.
Thank you.
Anybody not have it up yet? All right, you'll notice that this is showing you a front panel view of the NSM that I got up there. You'll see in the middle of the NSM, there's a bunch of lights there. This is the only place that the lights are at. Those are all LEDs and it'll tell you what to do. The biggest thing is when you are doing your checks and everything is said and done through the GUI, the big one is the top right LED. If the error light is on, it ain't working. You've done something wrong with the programming. So I'm going to scan down here. You'll notice we got some warnings and so forth and so on. Yeah. Introduction. This is 1.0. Scope 1.1. Just gives you an idea of what it is. It does. Physical description. Yeah. Here we go. General functional description. This is where it multiplexes all this type of data and then it talks about demultiplexes. Now with this in mind, it doesn't give you a whole lot as far as demultiplexing, but it does give you a plethora of information when it multiplexes. Just remember, anything it multiplexes, it has to demultiplex. Now, you can see 1.3.1.4 control computer interface. This is what you're going to be using where it says the NSM, the control computer. That's that GUI that you're going to be using in order to program it. And you're going to use either a 232 or a 422 DTE, Data Terminal Equipment. So there you have it. These are examples that we've been feeding you over the past couple of hours. So with that in mind, you can see Charlie, it says when using the GUI, that's that graphical user interface. In other words, it's going to come up with a program and you're going to be able to program through the use of tabs what you need to put onto the NSM. This gives you an idea. Now, whenever you're trying to figure out what each one of those set supports, for example, we showed you 6 different types, right? 6? Or is it 4? 6. NRZ, T1E1, CDI, and HSTV. That's 4. Man, I can't even count nowadays. Wow. So you can see Bravo under 1.3.1.5 external signal interface descriptions. You'll notice we have the NRZ must be balanced, where have you heard that term, RS422. It has a legacy mode and enhanced mode. You can see where we pulled the max data rate from the enhanced at 8.448 megabits per second. Well, wait a minute, you just said 8.44 megabits. It says kilobits. Well, I didn't say 8.448 kilobits per second. I said 8 point. Start to see there's interchangeability with these things. You got the T1E1, and here's where I like to point out some differences. It says AMI, which is alternate mark inversion, and it says Bravo 8 Zulu Sierra. What does that mean? Well, if you look that up on Google, you will find out that it is for the North American multiplexers, and it's a T1 line. If you look at the number 2, E1, is AMI or H or Hotel Delta Bravo 3. Believe it or not, you pull that up, This is either Europe or Japanese standards. And it's telling you where it's going to throw those zeros at. In our case with the T1, it's saying I'm going to throw the 9th zeros where the bit error rate or the bit violation will be. And on number 2, it's going to show you where the bit violation will be at number 4, 0. Now you don't need to know where the zeros get thrown. You just need to know that, hey, I know that that is zero suppression on the T1E1. It's self-clocking, isn't it? So everything we've gone and went over today is applied on the NSM. You got the group modem, better known as CDI, conditioned diphase. What's so different between conditioned diphase and all the other signaling formats that we talked about today? Let's see if I can pick on Airman Matei. See if he has an answer. And by the way, if you don't know, you can say you just don't know.
I just don't know, sir.
How about Zellers? Do you have an idea?
No, sir.
Okay, open it up for anybody.
Wait, sir, can you repeat the question? I didn't catch it.
Okay, the question is, what makes CDI so much more different than all the other signaling formats that we talked about today? Ready for it?
Yes, sir.
One word: transitions. It relies on transitions for its logics, for your signaling format, versus voltages on the others. Interesting. All right, so we're going to go down here to echo, and this is where we have the HSTV. You'll see it says EIA 530, where have you heard that? Or EIA 613, which is HSTV, high-speed serial interface. And you'll see that we've got the 52,000 kilobits per second, or 52 meg. And you can see something called secure order wire. Well, order wire, whenever I hear that, and you're going to hear this term a lot when we talk about the TISR, it is an auxiliary channel for maintenance. So just letting you know, I highlighted it for that purpose to give you an idea of what you're going to be dealing with later. And there's the computer, there's the external power cable. These aren't provided, you just got to get them. Theory of operation. Remember we talked briefly about purpose? Here's the full paragraph. And pictures are worth 1,000 words. You can see how simple this thing is. Got everybody coming into the multiplexer, and then out through the modem into the SATCOM, send it up to the bird relays it back down, and so forth and so on. This gives you a functional operation. I always like to highlight, I should have highlighted that one. It makes me laugh, but this is the NSM functional diagram shown below in figure 1-1. All descriptions below. MUX refers to multiplexer, and DMUX refers to demultiplexer. It just goes to show you what you got here. And this is, to me, again, a picture's worth 1,000 words. Figure 2-2, if you're having a hard time trying to figure out how many ports are on the Nodal satellite modem. We got network configurations. The reason why I highlighted this one, this makes it so much easier to give you like a point-to-point and the hub spoke, the mesh, and hybrid. It's probably one of the best ones I've seen out there. And then we start getting into user port interfaces and describing how many there is and what the connections are going to be. So you got 12 NRZ ports, you got 6 T1E1 ports. You got 6 group modem interfaces, better known as CDI, and then you got 2 HSTV interfaces. You can make them do what you needed to do with them. And there's your order wire. Just wanted to add that in there. This is what the rear looks like. Now, with that in mind, this piece of equipment isn't that big, but when you look on the back of the case is designed to break out everything. You can see that J3 has all of these, just one port for NRZ for 1 through 6. J2 is 1 through 6, J3 is 6 through 12. So it gives you an idea that, hey, I can connect up to 6 NRZ ports per J1, J2 and J3. You can see how this is all broken out when you take a look at the back of the case versus the actual back of the NSM. This is the front of the NSM, and it gives you all the indicators on the front panel and what they stand for. Again, the error light, if it is on, it's telling you don't have the darn thing programmed yet. You got to take a look at what you did to cause some grief like that. When you get on the GUI, you'll notice it says double click the NSM icon. This is the icon that it presents, and you can see that this is part of the GUI and how you start logging into everything. I think that is, yeah. And of course, going through the operation, the controls and indicators. I'm not going to go into that. It's really, you'll begin to know that as you start interfacing with it with the GUI. Is there any questions?